Hello and welcome everybody to this Hyperball talk about the Nancy Grace Roman Space Telescope. My name is Rebecca Hounsell and I'll be your speaker today. The Nancy Grace Roman Space Telescope. This is the top-ranked large space mission in the NASA 2010 Decadal Survey, and it will be following the James Webb Space Telescope. The spacecraft itself consists of a Hubble-class 2.4 meter infrared telescope with 100 times the field of view of Hubble. It is designed to study dark energy, exoplanets, and astrophysics in general. The satellite is equipped with a wide field instrument, which is noted here, a solar array sunshield, a service or spacecraft module, a coronagraph, which we use for technology demonstrations, and also has a high gain antenna, which is for fast data transfer. Now, one thing I do want to touch upon again is this fact that the Roman field of view is 100 times that of the Hubble. Now, what does this mean? So, here we have a video showing the pillars as imaged by Hubble. And these are, this is interstellar gas and dust in the Eagle Nebula, about 6,500 to 7,000 light years from Earth. And as we zoom out, we see that Roman will cover a significantly greater area, 100 times more in fact, and it is therefore a much more effective telescope. Now, one of the key scientific goals of the Roman mission is to get a better understanding of something we call dark energy. So what exactly is dark energy? Well, a long while ago, astronomers determined that the universe is expanding, meaning things are moving away from each other in all directions. However, this expansion was found not to be constant, but to occur at an accelerated rate. The only way for this to happen would be for some mysterious force, now dubbed dark energy, to be causing it. Dark energy is the factor needed to make our universal equations balance. Without it, we don't know how to account for the acceleration observed. This mysterious force was first noted through the use of type 1a supernovae. These are the explosive deaths of white dwarfs in binary systems. In these systems, the white dwarf obtains mass from either another white dwarf companion or some other less evolved star in the system. Once the mass of the white dwarf reaches a specific limit, known as the Chandrasekhar limit, a runaway reaction ensues, leading to the destruction of the system. Because the amount of energy released is very similar for each supernova 1A event, scientists can measure how far away the event was based on the brightness of the explosion observed. The further away these explosions are, the earlier back in time we're observing. This means that astronomers can measure the expansion of the universe and the rate that it is occurring through the observation of type 1a supernovae, and thus derive some knowledge about dark energy and its potential evolution. Astronomers use space telescopes to look at much fainter type 1a supernovae than ground-based can, and this is probing an era of time much less understood. Using Roman, scientists hope to increase significantly how far back they can observe the explosions and thus increase their knowledge of dark energy. Type 1a supernovae are therefore astronomy's most mature cosmological probes. An additional probe are baryonic acoustic oscillations. In the primordial universe, there were what we can think of as sound waves which rippled throughout the fabric of space, and these caused fluctuations in the density of the visible normal matter. So over time, galaxies tended to cluster around these peaks of the ripples, and patterns began to form. The overall effect of this means that for any galaxy today, we are more likely to find another galaxy about 500 million light years away than slightly nearer or farther. Another key objective of the Roman mission is to better understand something called dark matter. Dark matter is a form of matter that is thought to account for approximately 85% of the matter in the universe. Its presence has been determined through a variety of astrophysical phenomena, specifically related to gravitational effects that cannot be explained by our current understanding of gravity unless more matter is present than could be seen. For this reason, most experts think that dark matter is abundant in the universe and that it has a strong influence on its structure and evolution. Dark matter is called dark because it does not appear to interact with the electromagnetic field, which means it does not absorb, reflect, or emit electromagnetic radiation and is therefore difficult to detect. One way in which scientists have determined the presence of dark matter is through the examination of galaxy clusters. In these clusters, the space between galaxies is filled with a very hot gas, which can only be seen through the X-ray or gamma rays. By looking at the gas, scientists could determine how much matter was between the galaxies that wasn't easily visible. When they did this, however, they found that in order to keep the cluster together and not have the galaxies fly apart, that there had to be 5 times more material than was detected. This is a big indication of dark matter. This is the glue that's required to keep the galaxies together, and it's also thought to have been necessary for them to form in the first place, as indicated in the simulation we previously saw. The primary candidate for dark matter is a new kind of elementary particle that has not yet been detected. The particle cannot interact with normal matter or electromagnetic radiation, and as such has been dubbed weakly interacting massive particles, or WIMPs. Many experiments are in place to detect these particles and their effects, and one such experiment is Raman. While dark matter does not directly interact with normal matter, it can affect it gravitationally. We can map the presence of dark matter by looking at galaxy clusters and searching for an effect called gravitational lensing. When light passes by a large dark matter mass, it can be bent, and the light can be potentially magnified, causing an observer to see multiple images of the same galaxies with different brightnesses, all curved around the dark matter center. Raman is a sophisticated space mission and will look for weak gravitational lensing caused by smaller dark matter concentrations at distances never before probed. It will observe the lensing effects on a more refined scale and enable scientists to fill in more of the gaps with regards to this fascinating phenomena. An additional key objective for the Raman space mission is to detect new worlds, in particular planets that we would consider habitable, like the Earth. To do so, Raman will use 3 different observing techniques. The first we talk about, which is in the middle here, is direct imaging. This is direct observation of planets orbiting their host stars. This is very difficult and in most cases impossible, but Raman can accomplish this using the coronagraph that would help to block out the glare from the host stars. This method is good for planets that have large orbits and don't cross their stars. The second method we will talk about is microlensing. This relies on the fact that gravity can bend light. In this case, it is a subtle effect. Whereas one star passes in front of another, it bends the light like a lens, making it brighter. If the lens-making star has a planet around it, it makes the other star even brighter and produces the light curve you see in the far left panel. The final method we will discuss is the transit method. When a planet passes between a star and its observer, the light from the star dips. This is known as a transit and is another method of detecting exoplanets. Transits can help determine a variety of different exoplanet characteristics. The size of the exoplanet's orbit can be calculated from how long it takes to orbit once. The size of the planet itself can be calculated based on how much the star's brightness is lowered. Raman's instruments will allow for the implementation of each of these methods, and its wide-field of view means that we will detect a plethora of events. Raman's key objectives will be achieved through the implementation of 3 core surveys: the Galactic Bulge Time Domain Survey, the High Latitude Wide Area Survey, and the High Latitude Time Domain Survey. The Galactic Bulge Time Domain Survey is geared towards the search for exoplanets. It will also examine stellar variability and provide insights into the structure of our Milky Way. The survey will be repeated wide-field instrument observations over a set of fields selected for high stellar density and low foreground dusk obscuration within the galactic bulge. It will obtain light curve measurements of exoplanets, source star, and host star geometries over time. The notional microlensing survey concept cycles through 7 wide-field instrument fields, so about 2 square degrees total area. It will do so every 15 minutes through 6 72-day bulge seasons, when the galactic bulge is visible given Raman's orbital and pointing constraints. The High Latitude Wide Area Survey consists of combined imaging and spectroscopy over a common survey region using the wide field instrument. The imaging component of the High Latitude Wide Area Survey enables weak lensing shape measurements of hundreds of millions of galaxies, which yields precise measurements of matter clustering through measurements of cosmic shear, galaxy-galaxy lensing, and the abundance of mass profiles of galaxy clusters. There will be imaging for at least 1,700 square degrees in 4 near-infrared bands. The spectroscopic component of the High Latitude Wide Area Survey measures redshifts of tens of millions of galaxies via grism spectroscopy, again using the wide-field instrument over the same area as that for the imaging. The High Latitude Time Domain Survey consists of combined imaging and prism spectroscopy over a common survey region. There is likely to be an observing area in the northern and southern hemispheres with a cadence of 5 days and multiple tiers which focus on obtaining Type 1a supernovae at different redshifts. Thank you for your time. This is the end of my talk.